So we saw, what pHs did you use? 3, 5, 7, and 9, like that. And then what goes in the data table are the data you collected, right? This is absorbance, you read, right? So you put the thing in and you read it and you saw what happened. And basically what you should see happening is an increase in absorbance in all of these, right, as time proceeds, unless you got none to start with, right, which could be under extremes. Maybe you know, you fully denature the enzyme and you never get any of the reaction proceeding. So these might all be zeros or stay relatively low. But essentially, you're going to get this data table. And then if you graph this data table, either by hand or on Excel or whatever, you should be able to produce a table that looks like this, that has time as the independent variable, that has absorbance, and the units are ODUs here as a dependent variable. And this would give us, we did 4 treatments, 4 lines, right? We have a graph with 4 lines. And this could be, you know, pH 5, 7, 3, and 9, or something like that, right? Would give us that. Does that kind of make sense? And obviously, the real piece of information that we want is the rate of the reaction, right? And a rate is something changing over time, right? So it is, as Ting Ting mentioned, it's the slope. It's the slope of that line. So the rate of the chemical reaction at 5 is the slope of this best fit line at 5, and so forth. And the units are going to be change in optical density units. Well, per this case, second probably is how it would come out. And that's the rate. And obviously the one with the highest rate is going to be the optimal. Kind of makes sense, right? It's kind of logical. I can't remember the language I used, but if you make a graph of a rate, that's a derivative graph, and if you look at how that changes, ultimately what we wanted to produce was something like this. And this is the rate. This is called a derivative graph. And I can smooth the line look like that, which is kind of what, I mean, that's what we drew and showed on Friday. This is kind of the thing that we're looking at. So it's a multi-step process to produce this. This is the final product. This shows me the effect of pH on enzyme activity, at least this very specific reaction that I did. And obviously, wherever the rate's the maximal, that's the optimum. Could be broad, could be narrow, kind of depends, but there will be an optimum that we will derive from this. So this is the final product we're getting at. This is, I can't remember if people don't like the word derivative graph because nobody really knows what that means, I guess, unless you've done one before. So I might have changed the language, but a derivative graph is a graph of the rates. It is the graph, it is the final product that we want to see. It does show me the effect of pH on temperature. So my interpretation from this, you know, depends on the shape of the graph. It could have been, and I don't know what you get. Maybe you get something that's a little bit broader and then it drops off real quick like this or whatever. So maybe it's shifted toward the acidic range, and so it likes mildly acidic things, but as soon as you start getting basic, it doesn't like them. That's just something you have to figure out. I mean, obviously, from looking at that standardization experiment, I would expect the optimum to be somewhere acidic, right, slightly acidic around 5, because that's the conditions we did the standardization in. And then you would repeat the same thing, or you did, hopefully, repeat the same thing with temperature. Here, what's different here is not 3, 5, 7, and 9, but 4 degrees, 20 degrees, 32, 48, 99, whatever you did. And you're going to, again, produce the graph that looks like this. You need to calculate the rates. And you need to produce that kind of graph that shows the effect of temperature on that. And then the interpretation of these graphs has to do with trying to explain why the graph looks the way it does. You should use language and talk about things like denaturation, pHs of cell cytoplasm, temperature changing kinetic energy, and things like that. Right? Those are the interpretations of that, using that, the explanation of what we'll get there. And the inhibitor, I think you did, was either a plus-minus kind of thing. And so here you're just going to have with an inhibitor and without an inhibitor. And usually you're only going you won't really have a derivative graph that looks smooth like that. You'll just have a graph of the slopes. It'll be a column graph. This is rate, and this is with the inhibitor and without. whatever. I mean, you know, you understand the purpose of a table and a